Hi, I'm Antonio Sala. In this video, we'll give additional examples of conditional independence, in particular examples which are related to control concepts. If we review the formal definition, if we have three random variables, then B and C are conditionally independent when A takes a given value, or well, given A, if that happens for any value A might take. If information about C when A is known does not change my belief on the probability distribution of variable B. Or well, I just can swap B and C and say the same. Alternatively, if the joint probability or density conditioned to A is the product of the conditional probabilities, then they are conditionally independent. In a previous video, we explained the above idea in common sense interpretation, as for example saying that the power of a car, B, is statistically correlated with the average amount that the owner pays in speeding tickets, but that correlation could be explained by the speed when ticketed. So higher power implies higher speed implies higher fines, but I can split this explanation into two independent sub-explanations so that B and C are conditionally independent given speed. A second example describes two rolls of dice which were statistically independent, but if I knew their sum, then they became conditionally dependent. As a third example, height and having a college degree for a randomly chosen person were correlated, but the explanation of that correlation is that age was positively correlated with both of them, and once I condition to age, there is no remaining correlation between height and degree, so they are conditionally independent when age is known. A complicated version of this kind of diagrams is called Bayesian network in computer science. The next example we are going to deal with is measurement noise. This is more related to control, the objective of this second video. If I have a physical variable x, let's say a temperature, then, for instance, I may have an equation telling me that the measurement is the actual temperature plus some random noise, and that random noise is called measurement noise, and it's assumed to be statistically independent on everything, including itself in previous measurements. I mean, it's white noise. So there might be some other process variables, like another temperature, pressure, heating power, whatever, which are of course statistically correlated with the temperature I'm measuring. I may use the sensor to control the state of that process, but this white additive measurement noise assumption tells me that once the actual physical temperature of the tank, let's say I'm measuring, is given, then the measurement is conditionally independent to everything else in the plant, given the variable to be measured. So there may be a Bayesian network relating the other things. This will be the process model, but the measurement model is conditionally independent of everything given the temperature. Then the concept of measurement noise implies this conditional independence assumption. Now we can think of the statistical relationship between these other variables. So we will upgrade our model, and instead of having this measurement equation, we will add state and output equations as follows. We'll now consider this pair of equations. The first one is the state equation. When we have manipulated variables for control, we have sort of B, U, but as they are deterministic, we'll just omit them from the statistical considerations. So we have an evolution of the state in time and measurement equations. So this will be process noise and this thing will be measurement noise. We assume that double V and V are statistically independent of everything. They are independent, V and double V. They are also independent of X, and they are also independent on X, V and double V at any past instant. So they are white noise disturbances. So I can draw this kind of Bayesian network in which, these are other process variables, and these equations indicate that once I know xk, I can fully compute the probability distribution of xk plus 1 without knowing other present or past process variables or measurements or whatever, if I condition to perfect knowledge of xk. And likewise, if I know xk equal 0.723 volts, then this additive noise independent of everything allows me to compute the conditional probability distribution of yk, of the measurement, without needing any further knowledge on other process variable or other past values of states or noises. So this drawing depicts the underlying conditional independence assumptions that made me write these equations. If I know state now, I can sort of explain the behavior of my system by splitting it into a dynamics, prediction of next state, and then measurement equation, prediction of the probability distribution of measurements, and they are conditionally independent. And of course, that ends up in what is called the Markov hypothesis, underlying most dynamical models in physics when we have random inputs, in the sense that our understanding of the world, at least without, quantum entanglement and stuff like that, is that past influences future only through present. Formally, I can split my explanation of what I observe in time, saying that future and past are correlated, but conditionally independent given present. The only way for past to influence future is changing something at the present. So if no information about a past event remains or is recorded in any energy, book, or whatever thing that it exists now, then it cannot influence future. So that common sense idea is called Markov hypothesis in physics. And if the model is linear, it ends up in this linear state space equations in which xk is all present information, so that it's the only thing I need to predict the future. Everything from the past will be forcefully summarized in the state of my physical process, of my computer games or whatever, at the present time. So, as I mentioned, the idea of conditional independence is underlying the so-called Bayesian network paradigm used in computer science, artificial intelligence, etc., in which we have some random variables joined by arrows, and the absence of an arrow indicates conditionally independence. In many cases, this conditional independence is an assumption in the modeling phase to avoid me needing to compute a lot of conditional probabilities of covariance, in the sense that, for instance, my assumption that measurement noise is independent to everything else, etc. So these things allows me to simplify complex probabilistic models because I assume this kind of independence. And for instance, this is the Bayesian network associated with the simulation of this dynamical system model starting at time 0, k equals 0, discrete time. If I know x0, then I can split my computations between the measurement computations and the prediction of future state computations. If I know x1, so it happens. And so these Bayesian networks are graphs, a tree structure sort of, in which the arrows indicate that each variable is conditionally independent of everything other than its children, given its parents. So for instance, x2, once I give x1, is conditionally independent of all this stuff. Of course, the descendants of x2 indicate that x3, x4, and these measurements will be statistically dependent on x2, of course, but given x1, I can forget about x0, y0, y1. Likewise, given x3, statistical computations about x4 are conditionally independent of all this stuff. The full paradigm of this in linear models is the Kalman filter Rauchthun-Tribel smoother, and in general, in computer science, it's what's called as Bayesian networks. And it allows me explaining this propagation of probabilistic information in this sort of graphs, being conditional independence the key idea behind them. So let us conclude. The concept of conditional independence means that two statistically dependent variables seem independent when conditioned to a third variable, assuming it is known. Finding this conditional independence is key in science to explain complex probabilistic models in this kind of graph-based explanation, Bayesian network, and also it's important in science to avoid inferring spurious correlation or causality relationships. For instance, yellow teeth and lung cancer have strong correlation, but that correlation disappears once you condition to smoker or non-smoker. So smoking explains both yellow teeth and cancer, but suitable clinical trials or statistical evidence shows that once you account for smoking, then there is no remaining correlation between yellowish teeth and cancer. So if we didn't know this variable, then correlation between yellow teeth and lung cancer would make us recommend brushing the teeth with whitening toothpaste to avoid lung cancer. And that would be a wrong advice. So for instance, at the time of recording this video, we are at the end of the COVID-19 pandemic, and we see strong correlation between lethality and age. Of course, the one who discovers that lethality is due to the degradation of a given protein associated with whatever syndrome and the mutation of a chromosome, whatever, so that once we discover this, then age and COVID-19 lethality are conditionally independent, then okay, maybe he wins the Nobel Prize in medicine. As nothing is clear today about this explainer intermediate variable, then we just recommend people of old age to get 3, 4, 5, or, booster doses of vaccine. But, okay, clinical trials show it effective, so it's sort of better than, brushing your teeth to avoid cancer. That's why clinical trials are for, They are spurious correlations, just as the toothpaste stuff. And they are non-spurious in the sense that, okay, vaccinating old people seems to have beneficial effects in lethality. So, well, as I said, conditional independence is at the heart of modern statistical treatment of scientific data. The importance of this idea is what led computer scientists to build Bayesian networks, which is the construction of complex probabilistic models. And conditional independence is also at the heart of the Markov hypothesis, past can influence future only through present, and the concept of state in dynamical models in physics and control, and of course in the Bayesian filters, estimators, in control, digital signal processing, robotics, etc. So this is it. Thanks for watching, and to like or subscribe. Bye.